So welcome to the third and last part of this LXMLS 2020 warm-up or refresher, as you prefer to call it, about mathematical tools for machine learning. So the first part, which was divided into two segments, we looked at probability theory. In the last part, we'll look at mostly at algebra and a few other things at the end. So again, I'm stressing again that this is not supposed to be a course. It's kind of a should see these as a checklist of things that people who work on machine learning should know quite well. So as what should be considered as the fundamental background in mathematics for working in machine learning. Of course, it's not comprehensive. There are many other things which I will not cover, which are fundamental for machine learning, but we have no time to go over them. Namely, optimization is a fundamental tool that we will not touch upon. So, without further ado, let me just start with notation. So we'll mostly be dealing with matrices and vectors. So as probably most of you know, so just again, like I said, just a quick overview, quick flyover all these topics. So a matrix is a rectangular or square box of numbers with m rows and n columns. So it's for the real valued matrix, a matrix of real numbers. It could also be a complex matrix with complex numbers. And this is the usual notation for a matrix where A, I, J would be the element ij of this matrix. So row I, column J. So a vector in n dimensions is essentially just a matrix that has only one column and n rows. You can also have row matrices, row vectors. So vectors, column vectors, and row vectors are just particular cases of matrices. Although in some contexts they have a different specific meaning. So standard operations on matrices. So the transpose is simply corresponds to switching the indices that index columns and rows. So the transpose matrix at row I and column J is the same element that's in column row J and column I of the original matrix. It's flipped around the main diagonal of the matrix. I say that the matrix is symmetric if it equals its transpose. It's also, as you all probably know, given two matrices, we define their product through this expression. So the element ij, so row I and column J of the product of two matrices, is obtained by doing this sum. So this is essentially the product of the sum of all the products of elements in row I and column J. So row I of A, column J of B, and then adding across the free index that you get after freezing row I in A and column J in B. Inner product between two vectors is just the sum of the products of all the corresponding elements of the two vectors. It is only defined for vectors of the same dimension. You cannot define inner product between a pair of vectors that do not have the same dimension. So they need to belong to the same n-dimensional space. We'll come to this later on. And you can also define the outer product between two vectors. Now they do not have to have the same dimension. So you can have a vector x in n dimensions and the vector y of dimension m. And the outer product will be a matrix of size n times m, so n rows by m columns, where element ij of this so-called outer product is simply the product of coordinate component I of vector x and component j of vector y. So this is a way of writing, of obtaining a matrix just from a pair of vectors by computing the so-called outer product. So inner product gives you a real number, outer product takes two vectors, gives you a matrix. They go up or go down in dimension. So as we saw, given two matrices, we've already seen how to compute their products. So properties of the product, it's associative. So if you have three matrices that you need to multiply, A, B, C, you can multiply the first two, A times B, get a matrix, and then multiply that matrix by C. Or you can start by multiplying B times C, and then multiplying the result by A. The result will be the same because the product is associative. In general, it's not commutative. So it's not true in general that A times B is the same as B times A. In fact, you may be able to form the product A times B, but not even be able to form the product B times A. Notice from the definition of the product of two matrices that for the product of two matrices to be possible, the number of columns in the first matrix needs to be equal to the number of rows in the second matrix. So if the matrices are not square, these two, so this may not be even possible. So the transpose of the product is the product of the transposes, but in reverse order. All of these are very easy to check from the definition of product of matrices. Transpose of a sum is the sum of the transposes, which, okay, it's kind of obvious that it's true. So there are many special matrices. So probably the one that we use most often is the so-called identity matrix. So it's just a matrix that has ones along the diagonal and zero everywhere else. And this product has this matrix, the special matrix, has the property that it's a neutral element of the product of the matrix product. So if you multiply on the right or on the left some matrix A by identity, you still get A. Of course, this identity matrix here may not be the same as this one. So I'm not indicating the dimension of the matrix. So when you multiply on the right, this matrix needs to have the same dimension as the number of columns of A. Whereas if you multiply on the left, you need I to have the same size as the number of rows of it. A diagonal matrix is a generalization of identity matrix in the sense that it still only has non-zero elements along the diagonal, but these don't have to be zeros, don't have to be ones, I'm sorry, they can be arbitrary numbers. So if this is true, we say that we have a diagonal matrix. We say that we have an upper triangular matrix when all the elements below the main diagonal are zero, and vice versa, we say that we have a lower triangular matrix if all the elements above the main diagonal are zero. So these are special types of matrices. So maybe the most important notion to know about a matrix, one of the most important notions is the notion of eigenvector and eigenvalue. So what is it? So given some matrix A, if when you multiply it by some vector x, this is the same as multiplying this vector x by a constant lambda, by a scalar quantity lambda, then we say that x is an eigenvector of this matrix A and lambda is the corresponding eigenvalue. Notice that for this to be true, matrix A needs necessarily to be squared. There are no eigenvalues and eigenvectors for non-square matrices, because for non-square matrices, A times x does not have the same dimension as x, and so this would not be possible. So the eigenvalues of the diagonal matrix, of a diagonal matrix, are the elements in the diagonal themselves. I quiz you to think a little bit about what would be the eigenvectors for a diagonal matrix. It's easy to answer. So another important property number that you can compute from matrices is it's called the trace of the matrix. So the trace of the matrix is the sum of the elements along the diagonal. So for example, for a diagonal matrix, it's just the sum of those only elements that it has. For an identity matrix is simply n, because you have n ones along the diagonal, where n is the dimension of the matrix. And it can also be shown, and it's not so trivial, but it's not so difficult, to show that the trace, so the sum of the elements along the diagonal, is also equal to the sum of the eigenvalues of the matrix. So all the lambda i's that satisfy this property here. The determinant of a matrix is, by definition, the product of the eigenvalues of the matrix. And it's a very important quantity because you need it to compute the so-called inverse of a matrix. We'll see later what that is. So properties of the determinant. So the determinant of the product of two matrices is equal to the product of the determinant of the matrices. The determinant of the transpose is equal to the determinant of the original matrix. And if you multiply a matrix by some factor alpha, then the determinant of the product is alpha raised to n times the determinant of A. Just think of an identity matrix where the determinant is 1 because it's the product of the elements along the diagonal, which are the only elements which correspond to the eigenvalues. So for an identity matrix, you have 1, 1, 1, 1, 1 along the diagonal. So if you multiply by alpha, you have alpha, 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 alpha along the diagonal. So the determinant will be alpha to the n in the case of where A was an identity. So it's easy to convince yourself that this is true, although checking that it's true for an identity is not a proof. It's just to show that it's intuitively acceptable. Concerning properties of the trace, so the trace of the sum is the sum of the traces, of course, because it's just a linear operation, just corresponds to summing all the elements along the diagonal. And another very important property of the trace is that it is invariant under cyclic permutations of matrices in the product of any dimension, of any size of matrix. So the trace of ABC is the same as the trace as CAB. Notice that I did the cyclic permutation. I moved AB to the right and put C on the left. We can do it again. They can shift from here to here. You move B to the left and shift C and A to the right. A particular case of this is when you have only two matrices, A and B. If both AB and BA exist, so for if these products both exist, then the trace of AB is the same as the trace of BA. Inverse of a matrix. What's the inverse of a matrix? So given some matrix A, I say that it's invertible if there exists another matrix B of the same size, such that A times B equals B times A, and both equal identity. So if this is true, then we say that B is the inverse of matrix A, and I denote it as A to the minus 1, so A inverse. So some matrix A is invertible if and only if the determinant of this matrix is non-zero. So matrices with zero determinant are not invertible. And this agrees well with the fact that the determinant of the inverse is 1 over the determinant of the matrix, which immediately shows that this would not be possible to compute if the determinant was zero. So the inverse would not have a determinant because it does not exist. So solving linear systems. So if you faced with the need to solve a linear system, AX equals B, where A is a square matrix, an invertible square matrix, and only square matrices can be inverted, then X, the solution of the system, is A minus 1 times B. So the invert, you just compute the inverse of A, multiply on the left this equality. A minus 1 times A will just give you identity. So identity times X is just X. And on the right, you get inverse A times B. Properties of the inverse. So the inverse of the inverse is the matrix itself. So it's kind of pretty obvious. And the transpose of the inverse is the inverse of the transpose. So this is also easy to show. And the inverse of a product, if it exists, is the product of the inverses in reverse order. It's a little bit like the transpose, but in this case for the inverse. There are many algorithms to compute the inverse of a matrix. The general case, of course, there are slightly faster algorithms that explore certain properties of the matrices, and there are faster algorithms for general matrices, but the order of the cost is, without very specialized algorithms, is cubic in n. So it's a pretty expensive operation in practice. If any is of the order of thousands already, computing its inverse is already computationally heavy. Okay, so quadratic forms. So we've seen these, we've used these a lot when we talked about Gaussians. So maybe we should have started with this part of the refresher. But anyway, so a quadratic form given some square matrix A and a vector, the so-called quadratic form X transpose AX is simply the sum of all the products of pairs of elements from X, so X1 times X1, X1 times X2, and so all the products. And each of these products is multiplied by the corresponding element of matrix A. So this is called the quadratic form. It has a fundamental role in linear algebra and lots of applications in statistics, namely because it figures in the Gaussian probability density function. We say that a symmetric matrix is positive semi-definite if any quadratic form that you compute with it for any vector will always give you a non-negative quantity. In this case, you say that this matrix is positive semi-definite. And if it is strictly positive for any non-zero vector, then you say that it's a positive definite matrix. This is just a little slightly stronger condition than the one above. Again, it's easy to show that some matrix A symmetric matrix A is positive semi-definite if and only if all its eigenvalues are non-negative. So this is also a way of checking if a matrix is positive semi-definite. And the matrix is positive definite if all its eigenvalues are strictly positive, as you would expect. So let's get a bit more formal and talk about vector spaces, which also figure a very important tool to deal with mathematical, in a very important mathematical tool that's often used in machine learning. So a vector space over some field, and if you don't know what a field is, you can think of a field as a set of a set equipped with two operations that essentially work as addition and multiplication for real numbers. So, for example, the real numbers equipped with the common addition and multiplication is a field, but there are other fields. The complex numbers are also a field, and there are also Galois fields, which I'll mention very briefly later on. So, a vector space over a field is a set together with a pair of operations, operation of addition or plus, which takes pairs of elements from the field, from the vector space, and produces another element from the vector space, and another operation, which is called the product in general, which takes an element from the field and a vector from the vector space, and produces another element of the vector space. And for these set V to be called the vector space, this collection, this triplet of V plus and times needs to satisfy the following axioms. So the addition needs to be associative and commutative, which you know what it is. There exists an element in V such that when you add it to any other element, you get that other element, called the neutral element. For any x, there exists another element in V denoted as minus x, such that when you add it to x, you get 0, so it's called the symmetric element. There is associativity also when you multiply a pair of members, a pair of elements from the field by an element of the vector space. You can either multiply first beta by x and then multiply the result by alpha, and you can first multiply the two elements of the field and then multiply by x. It's the same. So the associativity is also applies to these kind of products that involve elements of f and elements of v. There is an element of the field, which is usually denoted as 1, which when multiplied by any element of v will give you the same element of v. And that element 1 needs to be the same, that does the same in the field. It needs to be the neutral element, so this is a neutral element of the multiplication. So the neutral element of the multiplication in the field is also neutral with respect to multiplication by elements of v. And finally, and that's where these two come together, there's distributivity of the multiplication by elements of the field with respect to summation, to the addition in the vector field. And there's also distributivity of the addition in the field with respect to multiplication by elements of the vector space. So these, either you can do the sum first and multiply after, or you can multiply inside alpha times x, alpha times y, and then add them together. So this has to be the same. This is a fundamental axiom down here that connects these two operations. So elements of V, as of course the name implies, the vector space, they're called vectors. Element of the field on which the vector space is built are called scalars. And we very often, and from now on, we'll use a more compact notation of dropping the dots for the multiplication and just keeping it as nothing, just putting them next to each other. Okay, so a couple of examples of vector spaces. So the usual vectors are vector spaces. So in Rn, so it's in the field of reals. If you build as vectors collections of real numbers, n-dimensional collections of real numbers in a certain order. So it's a tuple, it's not a set. The order makes a difference. So if you define addition as component-wise addition, so the addition of x plus y is x1 plus y1, and then the second position x2 plus y2, and so on. And multiplication by a scalar simply corresponds to multiplying inside every element of the vector. Then this is a regular, valid, and legal vector field. So real matrices of a given dimension are also a vector space with the usual matrix addition and multiplication by a scalar. This works exactly as for vectors. Of course, complex matrices also work okay. They're also a vector space. In a more or less standard example, although people from, say, know a little bit of communication theory and codes know these very well. So it's called the Galois field. It's a field with only two numbers, 0 and 1, where addition is defined as modulo 2 addition, meaning that 0 plus 0 is 0, 0 plus 1 and 1 plus 0 is 1, but 1 plus 1 is 0. You can think of this as the exclusive OR operation, if you think of ones and zeros in terms of bits. And the product is just a standard multiplication. So 0 times anything will give you 0, and 1 times 1 is 1. So if you do this, then this is binary vectors built on this so-called Galois field are again a vector space, and it's the fundamental tool to deal with codes in communications. So another less trivial example again is a set of all functions defined on some set but taking real values. If you define the addition between two functions as pointwise addition and multiplication by a scalar as simply pointwise multiplication, then this is a vector space in the sense that if you add two functions, you get another function, and distributivity holds, and all these properties. There are also other more constrained vector spaces of functions, but we will not talk about these now. Okay, what's a norm? So a norm is defined on a vector space. So a norm, which usually, as you know, is denoted by these pair of double bars around the arguments, is a function that maps elements of a vector space into non-negative real numbers that satisfy the three following axioms or properties. So for any pair of vectors and any scalar, this operation needs to be, this function needs to be homogeneous, meaning that if you multiply the argument by some alpha, you can move this argument outside by taking its absolute value. It needs to satisfy the triangle inequality, meaning that the norm of a sum of two vectors is always less or equal than the sum of the norms. And it needs to be defined. So the property is called definiteness. And it says that for the norm to be 0, the norm is 0 if and only if the vector is 0. So only the 0 vector can have 0 norm, and of course the 0 vector has 0 norm. So this is an equivalence. We say that we have a semi-norm if the two first axioms are satisfied, but not the third one. Classical example, of course, you all know, is the Euclidean norm. So the Euclidean norm is the square root of the sum of the squares of the components of some finite dimensional vector of dimension n. And we say that two norms, say norm and norm prime, are equivalent if there exist two constants, a alpha and beta, strictly larger than 0, such that for any vector, one of the norms is upper bounded and lower bounded, or upper bounded and lower bounded by alpha and beta times the other norm. If this is true, then we say that these two norms are equivalent. And in finite dimensional vector spaces, all norms are equivalent. It's always possible, given one norm and another norm, to find these parameters. So it can be shown that there exist these pair of parameters such that this is true. Other norms that are very important in these areas are the generalized Euclidean norm, the LP norm. So the LP norm simply generalizes the notion of Euclidean norm by, instead of computing the square root of the squares of the elements, it computes the p root of the sums of the p power of the elements of the components of the vector. But p needs to be larger or equal than 1. If p is less than 1, this is not a norm. But for p larger than 1, larger or equal than 1, these are all norms. And they are denoted as X norm P. So of course L2 with Euclidean norms is a notable case. The L1 norm is another notable case where you take the sum of the absolute values of the entries of the vector, and then you compute the one root, but the one root is just nothing, so you don't need any root. Another important one is the limit as P goes to infinity of this, which is called the infinity norm. And the infinity norm is simply the maximum of all the absolute values of the entries of the vector. And it's denoted as X infinity. This is also a norm, and it's also quite important and used. And finally, you probably hear about the L0 norm, which is not a norm because it's an LP type norm, but with P less than 1, so it's not a norm. But you can think of it as a limit case of these norms. But of course, when you're below 1, they're not norms, but these functions that you compute in this way. And it can be shown that as P goes to 0, this converges to the number of non-zero elements of the vector. So the zero norm of some vector, the so-called zero norm, which is not a norm, just counts how many non-zeros the vector, the components the vector has. It's easy to derive lots of equivalences. So for example, it's easy to show that the 2 norm is less or equal than the 1 norm, and the 1 norm is less or equal than the square root of n times the 2 norm. So there's lots of equivalences like this, and they're sometimes useful in proving inequalities, which is something that people that work in theoretical machine learning do on a daily basis. So another very important notion in algebra is that of inner products. So the inner product is a function that maps pairs of vectors into the real numbers. And this function, which has 2 arguments now, it's a function of 2 arguments, one argument, another argument, a vector and another vector, needs to satisfy these properties. It needs to be symmetric. So x in the product with y is the same as y in the product with x. It is bilinear, meaning that if you compute a linear combination of 2 vectors in a product with another one, this is the same as computing the same linear combination of the inner products of the vectors involved on the left side. So you can read it, it's self-explanatory. And it's called bilinearity because you, of course, this is true on the left argument of the inner product. It's also true on the right argument of the inner product because the inner product is symmetric. So, but we just need to specify it. So if this is true, together with symmetry, it's also true if instead of doing this on the left argument, you do it on the right argument. It's definiteness again. The property of definiteness, which happens for norms, also needs to happen here, which means that inner product of a vector with itself is always larger or equal than 0, and for it to be 0, you need x to be 0. So of course, 0 inner product with 0 is 0, but inner product is 0 if and only if, so it's an equivalence, x equals 0. A standard inner product in Rn is just we've seen this before, is just x transpose y. So sometimes people use these 2 notations interchangeably. It's just the sum of all the products of the corresponding elements of the 2 vectors. But there are many inner products in Rn. So for example, if you take a positive definite matrix, then this quantity, which is x transpose m times y, and of course, m and y have the same dimension because they're elements of the same vector space. So m needs to be a square matrix. So if this m is a symmetric positive definite matrix, then this is also an inner product, a valid inner product. Now, given an inner product, we can define a norm. So I'm asking, is it, because I've not shown that it is a norm, but let's assume for now that it is. Assume a norm as a square root of the inner product of a vector with itself. In this case, if you take the inner product as simply x transpose y, then the norm that this induces is just Euclidean norm, which is the square root of the sum of the squares. But if you take this other inner product with this inner matrix M, then the matrix norm, the norm that is induced using this matrix M is the so-called Mahalanobis norm, which is just the quadratic form involving x and this matrix M, which needs to be positive definite because you need these to be true. You need that definiteness to be true, and it also needs to apply to the norm. Okay, so more fundamental properties of inner products. So let's begin by noticing that if I compute the square of the norm of a sum of 2 vectors, because by definition, if this norm is induced by an inner product, then I can write this as the inner product of x plus y with x plus y. So now simply by expanding using this distributive property, so this bilinearity of the inner product, you can write this as the squared norm of the first term, squared norm of the second argument, plus 2 times the inner product of x plus y. So this is just a generalization to vectors of the famous formula for real numbers. A plus b squared is equals a squared plus b squared plus 2 times ab. And from this we can write down, so now that we know why this is so, it's easy to write down and to derive, actually, to prove the very famous Cauchy-Schwarz inequality, which states that for any pair of vectors, the absolute value of the inner product between them is upper bounded by the product of the norms. So it's less or equal than the product of the norms. So there are, if you look up proofs of Cauchy-Schwarz inequality on Wikipedia or any book, you'll find something that takes several paragraphs. But in fact, the proof is a one-line proof, which you can find in this very interesting paper, if you can read French. Proofs that make boom. It's quite easy to follow the proof. I'm not going to go through it, but if you take the time to read it, I think it will be very pleasing to see that you can show Cauchy-Schwarz in one line. It's just 3, 1 inequality, 1 equality with an implication, which is they're quite trivial. Okay, corollary of the Cauchy-Schwarz inequality is that, in fact, if you define a norm through an inner product as the square root of an inner product of a vector itself, then this is actually a norm because it does satisfy the triangle inequality. And this is easily shown through this chain of inequalities. So you just take this equality that we have up here, apply to this sum. Now you use Cauchy-Schwarz inequality to upper bound these inner products. And then you get that this is the square of the sum of the norms. And so you have that the norm, now you just remove the squares on both sides, and you get that the norm of the sum is less or equal than the sum of the norms, which is triangle inequality, which shows that norms induced by inner products are valid norms. Finally, Hilbert space, which also appears a lot in machine learning, especially at the time of kernel machines. The fundamental concept to understand kernel machines, support vector machines, is simply a complete vector space which is equipped with an inner product. And I won't say anything else about that. Okay, so basis. What's a basis of a vector space? So a basis of a vector space is just a collection of vectors in that vector space that satisfies the following thing. So they're linearly independent, meaning that the only way in which you can form a linear combination of these vectors to give you 0 is if all the weights in this linear combination are 0. So there are no cancellation. You cannot have a linear combination where some of these alphas are not 0 and still get 0, if this is a true valid basis. So they're linearly independent. And it has the spanning ability. This means that any vector in this vector space can be written as a linear combination of these vectors in the base. So basis is a collection of linearly independent vectors that span the space, meaning that you can write any vector in the space as a linear combination of vectors in this set of vectors. So in the compact notation, we say that V is the span of V. So the span of V is the collection of all the vectors that can be written as some linear combination of the elements of set V. So the dimension, by definition, the dimension of a vector space is the cardinality of a basis for that vector space. It's the number of vectors that you need to have a basis for that space. You say that we have an orthogonal basis if the elements in the basis are orthogonal to each other. So if any bi inner product with bj is 0 as long as I is not j. So all the vectors in the basis are orthogonal to each other. And if in addition to that they all have unit norm, then you say that you have an orthonormal basis. So it's a basis that all the vectors are orthogonal to each other and they all have unit norm. So that's what we usually call the standard, well, an orthonormal basis, the collection of vectors, all of unit norm and all orthogonal to each other. Okay, another collection of important names that you will see a lot when you look at mathematical papers in machine learning that deal with matrices are rank, range, and null space for these matrices. So if you take some real matrix of m rows and columns, the range of this matrix is by definition the collection of all vectors that you can obtain by multiplying a on the right by some vector x. So it's a collection of all vectors of size dimension m because a has m rows, such that there exists some vector in Rn because it have n columns, such that y equals ax. So this is just all the vectors that you can produce by multiplying a on the right by some vector x. Of course, this is a subset of Rm. It may be all of Rm, or it may be some subset of Rm. The null space of A is a subset on the other side. It's a subset of xm, of Rn, I'm sorry. And it's a collection of vectors such that when multiplied by A will give you 0. So these are vectors that will give you, when multiplied by A, an m-dimensional 0 vector on the m-dimensional, which is the size of the range space, because you arrive on Rm. So an m times n matrix can be seen as a mapping from Rn to Rm. Okay, so both range of A and the null space of A are vector spaces in the sense that they satisfy all the properties they need to satisfy to be vector spaces. For example, if you add two vectors in the null space, you still get a vector in the null space, it's obvious. Or if you get two vectors in the range space, you still get a vector in the range space, and you get, so all the properties of vector spaces are satisfied when you look at these two subsets. There's a very famous theorem relating the dimension of the range and the dimension of the null space of some matrix A, which says that the dimension of the range space plus the dimension of the null space equals n, where n is the number of columns of the matrix, that is the dimension of vectors that are multiplied by A on the right. A rank of a matrix is by definition the dimension of its range. So it's the dimension of the subspace of Rm that is spanned by considering linear combinations of columns of A. Notice that A times x is simply a linear combination of columns of A, where the weight of each column is the corresponding element of x. So every y is a linear combination of columns of A with weights given by vector x. So the dimension of the range space of A is always upper bounded by the minimum of these two quantities. Okay, the first one is obvious because you cannot have a space having a dimension which is a subspace of Rm cannot have a dimension higher than m, and the other one is because you only have n degrees of freedom because you're generating vectors by taking combinations, linear combinations of n vectors in which are the columns of A. So this is quite intuitively clear why this has to be upper bounded by the minimum of m and n. And from the dimension theorem, you can also say that the rank of A is n minus the dimension of the null space. So if the dimension of the null space is 0, then the rank of A is simply n, but for matrices that have a non-empty, non-trivial null spaces, then the rank is smaller than n. Well, a fundamental tool, you can actually almost devote a whole lecture or several lectures to this topic, singular value decomposition. And if you're familiar with it, good for you. If not, I urge you to learn about the singular value decomposition. So it's a fundamental topic in linear algebra and extremely useful for machine learning. And lots of tools in machine learning essentially boil down to computing very large SVDs of very large matrices. So suppose you have a rank R matrix. So now you know what rank is. We saw it in the previous slide, of dimension m times n. It turns out that the so-called singular value decomposition theorems state that any matrix of this rank and this size can be written as a product of three matrices with the following properties. So U is a matrix of size m times r. So m rows are columns where the number of columns is the rank of the matrix. The columns of U are an orthonormal basis of the range space of A. Okay, which means that you can represent any vector in the range of A as a linear combination of columns of U. And the columns of U, moreover, are orthogonal to each other and have unique norm. The columns of V are an orthonormal basis of the range of A transpose. Okay, so it's easy to understand what this is. It's just a range of, so if the range of A is the space spanned by considering linear combinations of columns of A, the range of A transpose is the linear space that's spanned by considering linear combinations of rows of A, because columns of A transpose are the same as rows of A. And finally, matrix lambda, the one that appears here in the middle, is a diagonal matrix that has of size r times r, where these quantities along the diagonal are called the singular values. How do you compute the singular values? So the singular values are the square roots of the eigenvalues of A transpose A or A transpose, which are the same. Okay. So this form that I'm giving you here is something called the compact form of the SVD, because I'm considering these matrices with the smallest size they can have for this to be true. There are other ways of writing this. So what do we mean by orthonormality of U and V? The fact that the columns of U are orthonormal to each other, and the columns of V are also orthonormal to each other, means that U transpose U equals identity. It's easy to check that. And V transpose V also equals identity. So they're orthonormal matrices, which means that if you transpose A, remember that the transpose of a product of matrices is the product of the transposes in reverse order. Okay, you get this expression that you have here. Of course, transposing a diagonal matrix doesn't do anything, but you can transpose V and you can transpose U and put them in reverse order. So visually, what does it mean? It means that any matrix of this size, m rows by n columns, which has rank r, can be written in this way. So it's starting from the right. You have a matrix that has r rows by n columns. So this has to be the number of columns need to be the same as the number of columns, because you're going to be multiplying this matrix by vectors that have size n on the right. Then the result of this product is simply scaled diagonally by this vector of diagonal of singular values. And finally, the resulting vector is multiplied by this matrix, which has r columns by m rows. So this is a visual representation of what we mean by what this U lambda VT does in terms of the sizes and shapes of the matrices involved. Another more geometric picture of these is that what actually the singular value decomposition is doing is the following. Suppose you're in R2, okay, 2 dimensions, and you have, say, a matrix of rank 2. So for a square matrix, when you multiply, say, this vector is one that have this basis with the red vector and the yellow vector. So this will be vector 1, 0. This is vector 0, 1. And multiplying by some matrix corresponds to maybe rotating and changing the dimension, the size of these vectors, okay? But this multiplication by matrix M, which should be A actually, can be decomposed into these 3 steps. That's what it says, multiply by VT, then by lambda, then by U. What does this mean? Multiplying by VT, because VT is an orthonormal matrix, this corresponds to rotating. So when you multiply by an orthonormal matrix, this always corresponds to a rotation of the space. Then you multiply by sigma. Sigma is a diagonal matrix. So what multiplying a vector by a diagonal matrix simply means changing the size of each of the components of the vector. So this means that I take this vector, the red vector, and I scale the horizontal and vertical components by scaling them differently depending on the singular values. So this will change both the size and the angle of these 2 vectors. And so they will, after you multiply by sigma, this is what happens to them. And then you go back to where you were, to the original space, by multiplying by U. But again, because U is an orthonormal matrix, this corresponds again to a rotation. Okay. So what the singular value decomposition shows is that multiplication by a matrix can always be seen as rotation, scaling, rotation. And it can always be decomposed into these triplet of operations in this specific order. So there are plenty of applications of single value decompositions, and it's a really fundamental tool in machine learning, and it's really a must-know thing in your mathematical toolbox. finally, I'm almost reaching the end. So we've talked a little bit about convexity in the first part when we talked about the entrance inequality. Let me just put this formally to just for the record. So convex sets. What's a convex set? Essentially, a convex set is a set such that when you join two elements of the set. So now I'm in subsets of our n, or I can even be in infinite dimensional space. It's quite abstract in this sense. To think of S as some Hilbert space. So it's a very intuitive notion that if you have a set and the set is convex, when you join this set, these 2 points, any 2 points in the set by a straight line, and this is what you're doing here. So lambda times x plus 1 minus lambda times x prime for any 2 points. It's called a convex combination of these 2 points. And as lambda goes from 0 to 1, you travel from x prime to x. And what this says is that any point along this line needs to be in the set, okay? So of course, this is a non-convex set because as you travel from x to x prime, you go out of the set. Strict concavity, or sorry, strict convexity demands that not only you are in the set, but you are also in the interior of the set. So for example, if you have a set like this, like say some polyhedric shape, this is a convex set, but it's not a strictly convex set because if you have 2 points on the boundary of the set, and if you join them, then these points along this segment are not in the interior of the set, they are on the boundary of the set, so this set is convex, but it's not a strictly convex set. Concerning functions, if we have an extended real valued function, what's an extended real valued function? It's a function that takes values in the extended real line, which is defined as the real union with plus infinity. There's some special number that you add to the possible values that functions can take. We say that the domain of a function is the set of points where the function is not equal to plus infinity. So some function f, some extended real valued function f is convex, if this is true. So we've seen these before. So we said that the function is convex if when you take 2 points on the graph of the function and you join them by a straight line, this straight line stays above the graph of the function. Actually, a more formal way of saying that the function is convex is to consider the so-called epigraph, which is the set of all the points that are above the graph of the function, and say that this set should be a convex function. And finally, a function is a strictly convex function if this straight line that joins 2 points on the graph of the function stays strictly above the graph of the function. So for example, a function like this, it's convex, but it's not strictly convex. So functions famously like the absolute value, which would be a plot like this, is a convex function, but it's not a strictly convex function. So you can read the definition slowly if you want. So it's again, convexity and the implications for optimization and for inequalities are again fundamental tools in the mathematical toolbox of machine learning. So this is it. So if you want a nice and quick overview of linear algebra from a machine learning applications perspective, I recommend this linear algebra review and reference, which again is used in one of the Stanford machine learning courses, and it's publicly available. There's most of the things that I talked about today are in there, but I've talked about other things that are not in there. And so I thank you for your attention, and I wish you a very nice 2020 LX MLS summer school.